everybody. So we are going to talk about, I think it's chapter 7. This is our second lecture, so chapter 7b really. It's all in one worksheet, but this is the second part of that worksheet. And this is going to be about solids and liquids. So a good start about understanding the difference between solids and liquids, which is kind of where we go on this question here, is to kind of think about, I don't know, let's say we have a cup and we put a piece of ice in it. So that's ice. And we have another cup, and let's say we put some apple juice in it or some other kind of liquid. And we have another cup, and you blow in it. Okay, so I don't know what that really is, but just pretend that that's actually a decent picture of me blowing something into a cup. So the ice is still in this cup. The juice is still in this cup. But is the gas still in this cup? Maybe a few of the molecules. But for the most part, it goes in, comes out, and then just goes and expands everywhere. Yeah, that's a really good drawing. That is why I was not an art major. All right, but essentially the ice sticks together, the juice sticks together, but the gas doesn't, it expands out. And if you're in my class, we've probably already talked about this, where when you're a solid, you're these stagnant particles. So let's say we've got like X, Y, X, Y, X, Y, X. So you're a solid and you're like all lined up and all pretty. If you have some kind of compound that's like XY. If you're juice or you're a liquid of any sort, these particles, you're still XY, XY, but you have the ability to kind of move around each other. All these atoms or molecules can kind of move around each other, but they're still sticking together. These guys, again, are pretty stagnant right next to each other, keeping the same distance from each other, depending on what kind of solid they are. These things are moving around, these particles are moving around each other, but they're still kind of held together by forces between them, which we'll talk about. And then we have the gas, which is like sayonara. It has no desire to be anywhere close to the other one. It has enough energy that they're just moving all over. And remember, these are variable in shape and variable in variable in volume. So, all right, what else we got? So we're going to talk about the forces that hold these together. What makes ice and juice different from a gas is that they have forces that hold them together, these molecules or particles. The first one we'll talk about is London dispersion. So, London dispersion forces are weak interactions between temporary dipoles. To remind you about what a dipole is anytime you have something on one area that has like what we call a partial negative charge, another area that has a partial positive charge. So if you have a molecule that has one area with partial negative and one area with partial positive, we say it has a dipole. Remember, electrons are negative, so essentially this would mean that electrons are over here and leaving this part with a positive charge over here, and that makes what we call a dipole, but it's like a magnet, right? So which molecules have these? Well, actually, let me draw an example. Let's look at carbon dioxide. Okay, so pretend we have a single molecule of carbon dioxide. This is nonpolar, right? You have oxygen pulling the electrons that way, this oxygen pulling electrons that way, because oxygen's more electronegative than carbon. We should know that by now. But it's not polar because they're pulling in equal and opposite directions. But let's say at any given point in time, electrons are moving back and forth, and for a brief second in time, maybe, just maybe, there's a few more electrons on the right side of this thing, leaving a few fewer electrons on the left side. And let's say you have another molecule that happens to, at that exact same time, have the exact opposite situation where more electrons are over here, creating a partial negative over here, and fewer electrons would be on that side, creating a partial positive. Now you have these little weak magnets, and that is what holds these carbon dioxides together. Which molecules have these? All molecules. What a great test question, I might ask. Like, which molecules have these? And the answer will be all, and it's going to be a pretty straightforward question. Then it asks for the type of force. Well, this would be a very weak force because these, again, this only happens spontaneously, and then maybe it shifts to the other side, almost even pushing them together, and then spontaneously comes forth. So this carbon dioxide, an example of when carbon dioxide might be a solid, would be if you had dry ice. So if you've ever taken dry ice, which is again made out of a whole bunch of carbon dioxide. So picture that this is a block of dry ice. They don't hold on to each other very well because these are very weak interactions. And that's why if you've ever put a block of dry ice, I wish I had some. I have an empty bag of it because it all evaporated and went into carbon dioxide gas. Sorry, my dog's eating the bone over here. Come on, buddy. Here, can you go in the other room? There you go. So the type of force, again, is weak. These are very weak interactions holding this stuff together. And then I give you a few different examples. Then we have dipole-dipole interactions. It says these are between permanent dipoles. So here, this was temporary. This only happened for a moment in time. But then we have things that have permanent dipoles. One of the things we'll talk a lot about today is water. And what molecules are going to have these are only polar molecules. So let's say you have water, HO. And if you remember, water's polar. It's got electrons moving up and towards this oxygen. Oxygen's more electronegative than hydrogen. And so the overall dipole will be like that, meaning we have a partial negative up here, and each of these hydrogens experience a partial positive. Okay. So if you have something like this, and you have another water molecule that's next to it, we'll flip it around. Again, the oxygen over here will have partial negative, this will have partial positive and partial positive. Think of this like a magnet. You have a negative and a positive. So these guys are going to be attracted to each other. And here you have a negative and a positive. So these guys are going to be attracted to each other. And it creates a bit of a stronger magnet. Another example would be, probably a better example, would be the one I listed, is this one. Now, just to refresh your memory, carbon and hydrogen, we pretend that there's no difference in electronegativity there. Those are not, there's no polar bond right there. However, in this overall molecule, oxygen's more polar than carbon. And to remind you how I know that, I probably should have done this at the beginning, is that things up and to the right of the periodic table are more electronegative. So oxygen's over here, which is more electronegative than carbon, and it creates this unequal pole. So oxygen over here is getting a lot of the electrons, therefore it's partial negative, this one's partial positive. Now we take this same molecule, and let's flip it around. Put the oxygen there, the carbon there, hydrogens, and it would be flipped, right? These are three-dimensional things, so if you've ever thrown some magnets down, they kind of align themselves. All right, so now we have this partial positive here with the partial negative there. These guys attract, partial negative there, partial positive there. Those guys attract. And the difference between this and what we did up here with carbon dioxide is that this was temporary. This is a permanent dipole. It's based on the fact that we have electronegative atoms in there, causing it to be polar. Permanent. So this happens with all polar molecules, and the type of force is medium. It's strong, but not, it's like kind of strong, but not super strong. And then I give you a few examples there, which we just did. Last but not least, we have hydrogen bonding. Hydrogen bonding is beautiful, but it only occurs and atoms that have a bond, an H bonded to an N in it, and then you can have something else that is, or I should have said molecules, when you have an H bonded to an N, an H bonded to an O, or an H bonded to an F. These are the only times you're going to have hydrogen bonding. If you have H bonded to a C, for example, that's not hydrogen bonding. Or H bonded to a Cl, that's not hydrogen bonding. Only H to N, H to O, and H to F. NOF, or fun, because chemistry is so fun. Okay, cool. So let's do an example of that. Let's say you have H, F, which is an acid, and you have another F2H. So in the same exact reason we were talking about before, if I give these guys all their electrons they're supposed to have for an octet, fluoride over here, this fluorine is going to have a partial negative, maybe this one with a partial positive. Again, how I knew that is the farthest up and to the right of the periodic table. Fluorine's way up here. It's super electronegative. So it's pulling all those electrons towards it. And this one has all the electrons going that way. And so these create the same kind of bond we were talking about. It's like two magnets, except for this is much stronger because fluorines, oxygens, and nitrogens, when bonded to a hydrogen, become pretty strong. They're pretty strong negatives, making those hydrogens pretty strong positives. And so this is a much stronger magnet than any of the other two examples we talked about. So which molecules have these? Again, anything with HF, HO, and HN. And the type of force is strong. Okay. Now that we know all that, we can do an example problem. This doesn't bleed through. Okay, so knowing everything that we know, let's go through and see how I might put this as a question, or maybe your homework might bring it up. Which species has the strongest intermolecular forces? In other words, the strongest forces between two of the same molecules, carbon dioxide or HBr? Well, let's look at carbon dioxide, and we should know how to draw it by now. Not because I drew it earlier, but because we know Lewis structures. And HBr. So we're going to go through and look at the individual forces. Does it have, let's look at carbon dioxide. Does it have London dispersion forces? If you remember, all molecules have London dispersion forces. So yes, it has London dispersion. Does it have dipole-dipole? In other words, is the molecule polar? Well, you have a pole going this way and a pole going that way, but they're equal and opposite. So it is not polar. It doesn't have dipole-dipole. Last but not least, does it have an HN, HO, or HF? The answer is no. So that's the only bonding it has is interactive force, intermolecular force it has is London dispersion. Let's look at HBr. Does it have London dispersion? Yes. Remember, all molecules will have this. Does this one have dipole-dipole? Remember, dipole-dipole interactions are for polar molecules, and absolutely it does, because bromine is up and to the right of the periodic table. So pretty much anything in the 7th column. So F, Cl, Br, I, all of these will create some polar bonds. So, and it doesn't have anything in the equal opposite direction pulling it back. So this has dipole-dipole. Dipole, not the Pope. All right, cool. So this is your answer because it has those weak forces and also medium forces. So HBr is your answer. Let's look at B, where it says, now compare HBr, which we know again. So we got HBr. We know it's got London dispersion. We know it's got dipole-dipole. because it's got that electronegativity right there. But the other option is HF. So HF, which has this pole right there, it's got London dispersion because all have it. I will ask it as a test question, I promise you, at some point. It also has dipole-dipole because this is polar. And it has hydrogen bonding because it's HF, HN, and HO. This doesn't have hydrogen bonding because it's not an N, O, or F. This has an F, and therefore it has hydrogen bonding. And that's why that's your answer for B. It has the strongest of the intermolecular forces. All right, higher intermolecular force means higher boiling point or melting point. So I'm actually going to skip over this part, and then I'm going to come back to it in a second. So let's see. Okay, so higher intermolecular forces mean higher boiling point or higher melting point. And hopefully that makes some sense. So over here, like let's say we have HBr, another BRH. And you got this force right here holding these things together. Now remember, this had London dispersion and it had dipole-dipole. Meaning the force that's holding these two things together is medium. But then we had HF and FH. Remember, this had London dispersion, dipole-dipole, and hydrogen. Meaning the forces holding these together are strong because it has that hydrogen bonding. So if you go, let's put them in a pot. So pretend you had a whole bunch of these molecules and you put them over a fire and you boil it. Well, these guys are only kind of holding onto each other, and these guys are holding onto each other strongly. Now, when you boil something, it takes that molecule and makes it a gas, right? So it goes off. So which one would be easier to let go of to become a gas? Well, the one with the least amount of force holding them together. Here, this H and this F are like, don't leave me, other H and F, don't leave me, and it's trying to hold on to them as it's boiling. So these guys will boil faster. In other words, you'll get HBr molecules as a gas, as opposed to these guys, which hold on tighter. So this will boil easier. In other words, at a lower boiling point. This is harder to boil. It's harder for it to become a gas, and it has a higher boiling point. And the same concept applies for melting point as well, where it goes from being a solid to a liquid. Okay, with that in mind, let's look at these two examples where it says which compound would have the highest boiling point. So we have NH3 and we have CH4. All right. So let's go through and list the forces that each of these has, because remember, the more forces it has, or the stronger forces it has, the higher its boiling point will be. So each of these has London dispersion, right? So it's got London dispersion, it has to. Next, this thing is polar. Remember, it looks like a triangle, where you got the hydrogen, 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 and nitrogen's up top. So this has dipole-dipole. In addition, it also has an HN, HO, or HF, right? It has an H and an N. That gives it hydrogen bonding as well. As opposed to the CH4, which has London dispersion, but it's not polar. All these, remember, carbon-hydrogen bonds are not polar. So it doesn't have any dipole-dipole, and it doesn't have any hydrogen bonding. So this only has London dispersion, meaning this one has the most things holding it together, so it won't want to boil. And therefore, this will have a high boiling point. It'll take a lot of energy to make it boiling. And NH3 would be your answer. All right, the same concept applies for a melting point. So here we have CH4O. And CH3Cl. All right, so they both have London dispersion. This one is electronegative. It's got this oxygen pulling it this way. This has dipole. This one also has dipole. Remember, chlorine's in the 7th column, so it's pulling electrons that way. This one's got that. So it has dipole. But the difference between them is this has an OH, an ON, or an OF. It's got an OH. So it's got hydrogen. And this one has no hydrogen. And that's why this one is going to have the higher melting point. Higher melting point. It'll turn into a liquid more easily. All right, now let's go back up here. Let's look at this one. I'll throw my dogs out. Okay. Propane versus butane. So propane, by the way, is C3H8, and butane is C4H10. So if we draw these things out, versus remember, carbons like to have 4 bonds, and this is why they look like this. They all have 4 bonds on them. Okay, so you got these 2 molecules. Let's go through and list, because it's asking which one has a higher boiling or melting point. Let's go ahead and list what forces they have. So this has London dispersion. This is London dispersion. Do either of them have dipole? Remember, carbon-hydrogen bonds aren't electronegative. Carbon-hydrogen, not polar, I'll say. That's probably a better way of putting it. Carbon-hydrogen bonds are not polar. So this is all carbon-hydrogen, so it's not polar. This is all carbon-hydrogen, it's not polar. So the question is, which one's going to boil? Well, if you can imagine having a pot full of these things, and another pot here, and we put some fire under it, so pretend you got this kitchen pot, and it's cooking both of these. The one that's the most difficult to make into a gas will be the heavier one, because just like in life, it's hard to lift up heavier things and get them going. So this one is easy, it'll boil first. This one will boil second because it's bigger. Bigger. It will have a higher boiling point and higher melting point. Something to think about is, even if you didn't know how to draw these, because I know that kind of throws people off. If you knew propane versus butane here, we would know that this has 3 carbons and that has 4. This has 8 hydrogens, that has 10. So you automatically know that this one's more massive. It has more stuff in it. Because it has more stuff, you know that its molecular weight, for example, will be higher. Therefore, it's bigger and harder to pull off. All right. Let's move on to vapor pressure. So So vapor pressure is something we've actually already discussed without really fully discussing it. Let's go back to our example of carbon dioxide. Let's put 2 carbon dioxides in here. And put them in a pot. So pretend you got some dry ice sitting inside of a pot and you're heating it up. Now keep in mind there would be more than 2 molecules in there, right? There'd be billions upon billions upon billions of molecules in a small sample of dry ice. And over here, let's put some water. Let's boil that sucker too. Okay, so if you're boiling dry ice and you're boiling water, dry ice will boil really, really fast. We already know it should have a lower boiling point because dry ice only has London dispersion forces, whereas something like this has London dispersion, dipole-dipole because it's polar, and hydrogen. Meaning the forces holding them together. I had never written this out, so maybe that will help. Holding these molecules together are strong. So water, this water does not want to let go of that water. That water doesn't want to let go of that water. But here, carbon dioxide's like, sayonara, see ya. So water is going to bond up like this, where that hydrogen is attracted to that oxygen, because remember, oxygen is electronegative, that oxygen is attracted to that one, that's attracted to that one, that's attracted to that one. It builds this beautiful network of stuff, and actually this is what surface tension is, the network of a bunch of water molecules attracted to each other, which allows spiders and things to walk across. As opposed to this one, which is very, very weak. And again, these are strong interactions holding them together. So if you put a lid on this pot and you start heating it up, my question to you would be, which one would fill with gas first, the left or the right? And hopefully your answer is the left, because again, these are weak interactions, so carbon dioxide wants to go away. It wants to become a gas. There's nothing holding it together, keeping it a liquid or a solid. So you'd have a lot of gas molecules over here. And we call that, the gas that's kind of hanging on top of the liquid, we call this vapor pressure. Because remember, gases create pressure. So if you have more gases up there pushing against the sides of the lid or whatever, it's going to have a higher vapor pressure. So this one would have higher vapor pressure, as opposed to this one, which would have a lower vapor pressure. It doesn't want to become a gas. All right, so hopefully that makes some sense. Remember, this, just to clarify, this would have a lower boiling point and a lower melting point. These two go together, and this one will always be the opposite. So this would have a higher boiling point and a higher melting point. It's more difficult to boil that stuff off, and therefore there will be less of a gas there. All right, so it says, which one has a higher boiling point? Well, let's see if we can answer this now. We have H2S and H2O. This one also has electrons right there and there. So each of these has London dispersion. Each of these is polar. It's got dipole-dipole. But there's one difference between them in that this has a hydrogen-oxygen. It's hydrogen bonding. In case you missed that, again, that's anytime you have an HF, HO, or HN. this is not an N, O, or F, and therefore this doesn't have hydrogen bonding. So this one has a higher boiling point. That means this one will become a gas more easily, and this one would have the higher vapor pressure. Remember, they're going to be opposites. That would be my answer for that. All right, moving on to solid states. Okay, so solids are either crystalline, which have a regular arrangement, or amorphous. So let's say you had some kind of compound that was like A, B, and we'll call this one's crystalline, crystalline, and we have another A, B, we'll call this amorphous. Both of these are solids. So I'll put a little S after it to indicate that it's solid. So we got AB solid, which is crystalline, and AB solid, which is amorphous. So in the crystalline, these things will be nice and ordered. You can just picture like a crystal, which are very pretty, right? In order to get a crystal, generally things are going to have the same distance between each other inside of a crystal, and everything will be nice and ordered. Amorphous is like if the crystalline got sick and threw up. And you can see there's no real pattern. There are different distances between each other. And this would be an amorphous solid. So example of crystalline would be any kind of crystal that you see. Anything that's generally really pretty will be crystalline. And there's other things that you can't see through, but that are also crystalline, that are highly ordered. And we have something like amorphous, like rubber is an amorphous solid, where it's not very pretty. It's kind of all over the place. Light can't travel through it very easily, and therefore it's not very pretty. So I just wanted to cover that. We're only going to be focusing on crystalline today. I don't even think your book covers amorphous, but I thought it was important to talk about the two different kinds of solids. Okay, so solids are either crystalline or amorphous, and again, we're talking only about amorphous. So for ionic crystallines, remember, ionic are made out of a metal and non-metal on the periodic table. And in case you forgot that, your final exam's coming up soon enough, you should probably remember that you got this stair stepper like this. These over here are metals. These up here are nonmetals on the periodic table. So if you have an ionic compound, chances are when it is a solid, it will form in this fashion. So an example most people like to use is like NaCl. Remember, Na has positive charge and Cl has negative charge. So if it's a crystalline solid, it'll look something like this. Nice and highly ordered. I just kind of thought of an idea to do a little demonstration. So I'm going to do that here. I'm going to write it here instead. This was Cl minus, Na plus, Cl minus. Cool. So you can imagine that this is one beautiful three-dimensional structure, maybe. So imagine that it goes all the way back just like this, and it's really pretty, and that's why salt, for example, is super pretty. If you've ever actually held some table salt in your hands, it looks really nice, and it's very crystal in nature. Now if you take a hammer, let's see, let's say you take a hammer that has a really small handle. Okay. Kind of looks like a hammer, kind of not. But pretend you got a hammer and you hit this thing. one interesting fact about ionic crystalline solids is that if you hit them, so this chlorine is going to move down here and align with that chlorine. And remember, negative and negative don't like each other. So what it's going to do is push away. So again, if you hit it with a hammer, it's going to go down. It's going to push away because the negative and positive don't like each other. And you'll get a crack. Kind of cool, right? And so that's why if you hit ionic compounds, you'll crack them or fraction. We'll talk about how that's different from other things in the next ones. All right. Then we talk about molecular compounds. A little harder to draw, but this would be if we have any kind of thing that's 2 or more nonmetals. So molecular, it's just saying it's covalently bonded, 2 or more nonmetals. So this would be if you have like a C6H12O6, some glucose. And this would be like sugar, and sugar makes beautiful crystals as well. But it's different because these carbons, the 12 hydrogens and the 6 oxygens are all molecularly bonded into a beautiful sugar structure. So let's pretend you have a beautiful molecule over here, and next to it would be another beautiful molecule. And under it would be another beautiful molecule. And another beautiful molecule. Now, if you hit these with a hammer, they don't care. They're not going to push away from each other. But they're not going to push away from each other because they're not attracted to each other. They're not going to be opposing each other. And so it's okay if you hit it, it's not going to cause this crazy fracture, but it'll generally have more of a jagged edge as opposed to the ionic compound, which would have been a smooth edge. All right, we have network solids. And network solids are something only your book likes to cover. Because it's a difficult topic to discuss because you can't really know exactly when something is a network solid unless you know. So an example of a network solid would be like SiO2. So in the case of SiO2, for every silicon, there will be 2 oxygens. And the crazy thing about this is every single atom is bonded to another atom. So it really creates almost like a molecule in and of its own. So this SiO2 only tells you for every 1 silicon, there's 2 oxygens. And then you'd have like silicon up here. Anyways, hopefully you can kind of see how this works. But these are actually covalently bonded, and it creates a very, very strong network. This would actually be like glass, creates a strong network. Another example would be diamond. So diamond will actually covalently bond like this to 4 other carbons. And we call this a lattice structure when they look like this because they look like a fence lattice, right? But hopefully you can get a general idea here of how they kind of look, but they're all bonded to each other. And we know that diamond, so we write that as carbon solid, and usually they'll subscript it down here, diamond, as opposed to graphite, which would be an amorphous solid, and it wouldn't have any kind of structure like this. So diamond is super strong, right? And we know that because we use it in saws, for example, in saw blades, because it can cut through almost anything. And the reason it's so strong is because it's got all these covalently bonded networks, and covalent bonds are decently strong, especially when you have them in massive amounts. So this is pretty cool stuff. But I don't believe that your homework has a question where network is an option. I don't believe it's ever the answer. Because again, I would really want you guys to look it up, or I would tell you if I ever came across a network solid. Last but not least, we have metallic. So metallic's made from metals. An example of metallic would be something that's only a metal. Only one metal. So for example, lead, copper, silver. And here's how it would look. Silver, silver. So if it were in a three-dimensional structure, it looks like this. Now these are held together by a group of electrons that are essentially freely moving around it. That's an interesting kind of new age study in and of itself, is how those electrons hold everything together. But when you see a metal, like a copper wire or something like that, it's generally held together like this, where they're hanging out and electrons can move around. And in fact, that's what makes them conductive at the end of the day, is that those electrons can move. But if we were to take a hammer and hit these guys, let's see, how can I do this? I already failed you. Let's do this. It's a slightly better hammer. So if you were to use a hammer and hit these guys, what would happen is, instead of falling down and cracking because they're opposites, these are all the same thing, and they're not going to be interested in breaking apart from each other. So when you hit a metal with a hammer, all you do is just like force that silver in there, and you get a dent. And that's why metals dent, because they're not, when you push them together, they're not going to have like a positive and a positive to push each other apart, or a negative and negative to push each other apart like we did with the ionic. Instead, you're just going to get a dent. And yeah, hopefully that makes some sense. And if it doesn't, well, you can talk to me in class. And I think that's everything. Woohoo! Oh, all right, it is coffee time for me, and I hope it is study time for you, suckers. Just kidding. All right, guys, have a great day. Talk to you later. Bye.